Nathanson. She's going to talk about tropical fans and normal complexes. Go ahead, Anastasia.
Thank you, Ahmed. First of all, thank you for organizing. This has been a really fun seminar for me to attend. And also for those of you coming from the US, extra thank you for coming on the holiday. I really appreciate it. It's Thanksgiving in the US, so you know, I'm in California. It's noon here. It's easy for me. Okay. All of that. So I'll be talking about tropical fans and normal complexes today. This is I'm going to be explaining the main result of my paper with my co-author Dustin Ross and my also co-author and master's thesis advisor. The goal is to understand the meaning and the statement of this theorem, which is the culmination of everything we did there. It reads that for any pseudo-cubical value Z, the volume polynomial is the volume of the normal complex. All of these are, you know, a lot of these words are new, so all good of these words are not making sense. The whole, the whole talk is to explain all of these words. We'll talk about them in detail. In short, what this theorem shows is that the volume polynomial here on the left has a real volume on the right. Maybe this talk would be more accurately named putting the volume back into the volume polynomial. I have a choice of two. I chose with one. Maybe this would have been better, but that's kind of the goal, is to put the volume back into the volume polynomial. That's the guiding principle of this project. We'll do so by looking at the case of complete fans and use that as our inspiration to expand the known structures on the complete fans to tropical fans. And along the way, this is a Matroid seminar. I will be talking about Bergman fans of Matroids, after all. The way this is going to go is I'll talk about some background. I'll talk about complete fans. I'll talk about normal complexes, introduce what that is, and then we'll talk about this volume, real volume, and then we'll use Bergman fans at the end. So fans is in the title. What is a fan? When I say a fan, I mean a polyhedral complex made up of cones living in the ambient vector space NR. I don't want to assume too much about my space. It's just some NR. I'm denoting the subspace generated by a cone as n sigma r. So I'm going to use little sigma for cones, big sigma for fans. We assume that our fans are pure of dimension d, and I'm denoting k-dimensional cones by the sigma parenthesis k. So that means that we'll frequently see this notation, sigma parentheses d will mean top dimensional cones. I'm assuming that all cones are simplicial, so the dimension of the cone is just the number of rays that generated. This also means that the rays are going to be linearly independent. That's nice. We'll use that at times. I'm also going to denote, I'm choosing ray generators as u rho for every non-zero ray. And I'm choosing that, that's what it'll mean this vector. We have two examples of cones here. The simple looking one on the right consists of 4 cones. Even it has the one top dimensional cone, but it also has 2 rays and then 1 vertex. And so it's 2-dimensional cone. It lives in R2. And here I have another 2-dimensional cone, this small one at the bottom, but now it lives in R3. We can see that it's 2-dimensional because its top dimensional cones are these planes that are generated by 2 rays. We'll see this picture a lot more in the future. Don't worry about it too much. We'll also be talking about the Chow ring of a fan. It's a graded ring with a variable for every ray of the fan, quotiented by variables corresponding to non-faces and the sum of linear functionals on each ray. Without the J ideal, we have the Stanley-Reisner ring. Maybe that's a familiar structure to some of you. And maybe you've seen a different description of the J ideal. This is the Fechner-Niedzwiecki definition that works for all fans. Adibra Sitoha and Katz have a nice definition in their paper, but that one is for Matroids. So I'm staying away from that one for now, because I want to describe fans that don't just relate to Matroids. I'll use this X sigma to denote just like, the sum of all of the rays that are in that fan. It's exactly what we want it to be. So the titular character, tropical fans, it's defined by the balancing condition, which is that if I take out a codimension 1 cone, I'll name it tau here, the ray generators of the top dimensional cone sigma that contain tau is within the subspace generated by tau. So it's a lot of words. Let's look at this picture. I have, this is a 2-dimensional fan. So my codimension 1 things are rays. Let's look at this ray. The subspace generated by it is just, the ray itself. And all of these cones go through, we can see in this cross section, they go through exactly, they all meet at this ray. I have weighted here in parentheses. Tropical fans allow weights. The only thing, we are only going to use weight 1 for this talk, so I don't want to focus on the weighted condition too much, but we can imagine a weight function defined on every top dimensional cone, multiplying this sum here. Tropical fans can also be characterized by us being able to find a well-defined linear map called degree that's going to take in the top dimensional cones and just assign the number 1 to them. We care about this degree function because it defines the volume polynomial, something that's been well studied and something we want to reinterpret. So the volume polynomial is going to take in the divisors of the Chow ring, which are going to be linear polynomials in generators x row with 0 coefficients. It's going to take them in, it's going to put them to the highest degree possible, D, and then it's going to take the degree map of it. So puts them to the appropriate dimension for the degree map, gives 1 to all of the top dimensional cones. It's not obvious that, this construction feels a little arbitrary, like, okay, we have some degree map, but one of the big results of Adibra Sitoha and Katz is that the volume polynomial fully characterizes the Chow ring. So, this little, this construction actually tells us a lot and holds a lot of structure in it. But there's something funny about this definition, which inspired this whole project. Why is the word volume in here? So our goal is to provide a geometric meaning to this algebraic object. And what I mean by that is we want to find a polyhedral object whose volume is calculated by the volume polynomial. So far, we've talked about this left side of, yes.
Oh, so in the previous slide, I just had a question.
Yeah.
So in the map on the left bottom, is it the map to the integers or to the polynomial ring?
Oh my God! It should absolutely be the integers. Thanks for catching that. Yeah. Yeah, absolutely. But it will be a. Oh wait. No. I take this back. This is the map to the integers. This will give us. Sorry, I jumped too hard. Okay. This is going to give us, this degree map acts on the x's, but we're left with the z's. So it will give us a polynomial in these 0 variables.
Okay. So linear, like you can take the z's out, right? Okay, I understand.
Yes, exactly that. We'll see an example shortly. Okay, so it is known we've talked about this left side, which is the volume polynomial of tropical fans, and we hope it computes the volume of something. This is going to be a polynomial in these 0 variables. I'll call z sometimes our coefficient vector. So the z, just because it's a bunch of coefficients on our x's. Now, let's talk about complete fans. A complete fan is such that all of NR is contained within a cone of the fan. So here, this example cone lives in R2. We can imagine everything in this two-dimensional space is contained within some cone here. The degree map exists here. So the volume polynomial exists just as before. It's going to be a homogeneous polynomial. We can rest assured that that complete fans are a subset of the family of tropical fans. And maybe we can also convince ourselves of that if we look, if we try to check the balancing condition here. I can take away this ray and these cones will still contain that. Let's calculate the volume polynomial for this fan. My Chow ring should have 6 variables for all of the 6 rays. Here, I have 3 here, 3 here. And here are the variables for them. The I-ideal consists of degree 2 monomials that don't correspond to faces. So for example, x1, x0, there's no cone that is generated by ray 0 and ray 1. And this has some linear functions. The volume polynomial takes in this linear polynomial, squares it, and takes the degree map to give us this. Let's see how we got this. The mixed term monomials that we see here always correspond to faces of the fan. So let's take 1, 2. Here's the face between rays 1 and 1, 2. How we get to this coefficient of 2 is that, I have a mixed, this is a mixed term monomial in the square. So I have to have this coefficient of 2 outside of it. I take the degree map here, exactly as you said, Ahmed. I pull out the 2 z's, and then I'm left with the degree map on x1, x2, which is 1, because that's a top dimensional fan, or top dimensional cone. For the squared monomials, and all of the mixed term monomials that don't correspond to a face live in this ideal. So those are gone. For the square monomials, we get them when we are taking the degree of something like z1 x1 squared. I can pull out the z1 just the same, and then I'm left with this x1 squared. The degree map doesn't know what to do with that, but we can use the equivalences in the second ideal to rewrite one of the x1s in terms of these variables. So here we rewrite x1 by x2 plus x02 minus x01. I distribute the x in, it's a linear map, everything works nicely. So x1, x2, not a face, x1, x02, not a face either, but x1, x01 is a face here. So the degree map gives it 1. I can pull out this coefficient of negative, I can pull out this negative to get the coefficient of negative z1 squared. And that's how it's going to work for all of these square monomials and all of these mixed term monomials. We have a lot of equivalences in this ideal, but things work out beautifully to, no matter what rewriting I choose to do of x1, it's all going to be equivalent. A complete fan has something called a normal polytope. It's the set of vectors in the dual space whose inner product with the ray generators is less than the z associated to that ray. This is a normal fan. For our example fan, we can see that the z values here define boundaries at each ray. So this z12 lives, it's orthogonal to the ray 1, 2, and it creates a boundary here. So sometimes I'll call these bounding values, bounding variables. The normal polytope is made up of half spaces defined by this coefficient vector. Half spaces live in the dual space, and I'm taking these vectors from the dual space. So for complete fans, this is not usually emphasized. I mean, a normal polytope, that's something that's been known for many years. Because the support of the fan is the whole space, the choice of inner product is not necessary. We can kind of just use the ambiguous inner product. But in order to draw this, we need to identify the vector spaces, the dual space and the original vector space. To draw it, I have to choose a basis. So we did choose the dot product here and chose a basis. What is it? 1 and 2. It's a well-known fact that the volume polynomial of a fan calculates the volume of its normal polytopes, under this condition that the normal fan of this normal fan is the fan itself. So volume polynomial calculates the volume of the normal polytope. And here, I mean that super literally. This hexagon, its area, it's a two-dimensional thing, its area is exactly this polynomial that we found before. So, you can take a screenshot, you could play around with it. You just have a rectangle, take away 2 triangles. You should be able to recover this exact formula. So now we've seen a particular case where the equivalence of this theorem is true. And what I mean by that is we have a polyhedral object whose volume is calculated by the volume polynomial. I say polyhedral here, but we really want something polytopal, right? I don't want something infinite. I want something nice and bounded. This is a long known result from the 70s. We now want to generalize this to non-complete fans. And we're stopping the expansion of tropical fans because that's where the volume polynomial makes sense. We do so by introducing an analog of normal polytopes that we'll call the normal complex. Now that we're looking at not complete fans, our top dimensional cones don't describe the whole space that we're in. So it doesn't make sense to define the polytope on the whole fan. So we restrict ourselves to defining polytopes on each cone. But because the cones are of a smaller dimension than the space, there are too few boundaries to define a polytope. We can see with this one, I would have, this is a 2-dimensional cones. These 2 boundaries will only define a plane with this bump in it. So, but I want a polytope, right? I want a bounded shape. So we have to intersect. I'm going to adjust this definition by intersecting this polytope with the cone itself to make sure it's within the cone. Now the choice of inner product becomes non-trivial. These half spaces, this lives in the dual space. The cone itself lives in the vector space. If I want to talk about intersecting them, I have to have this. I have to choose the inner product to have an isomorphism there. So I adjust this definition again. I'm going to make my choice of inner product known here by putting it in the definition. So it's a polytope with respect to the inner product. And then I take the inner product and then I intersect. So I find these half spaces, I take their intersection. I first take the inner product, then I take the intersection with the cone. And that's how I'm going to get these polytopes. And I want to make this inner product choice very apparent because it completely determines the shape of the polytope. So we're going to define a normal complex of a not complete fan by taking the union of polytopes defined on each top dimensional cone of a fan. So here we have this two-dimensional fan living in R3 that we saw earlier. This fan has 9 two-dimensional cones and 8 rays. We take the union of 9 polytopes to get this normal complex. Here we can see that the Z values still do the same thing. They bound at each ray, and we get this shape. So we found a polytopal object based on a non-complete tropical fan. It has the same bounding variables. This feels like this claim should be true, that the volume of the normal complex is computed by the volume polynomial. There's a little bit of care that we need to take with the way we choose the Z values. Even on this normal complex that we saw earlier for a complete fan, I can decrease one of the ZIs, this was Z1. I can decrease it, which will push this in to give us this, which is not even a complex. So I'm going to require a condition we call cubicalness to prevent this from happening. We're going to define this vector W associated to each cone. That is going to be the vector whose inner product with all the ray generators is exactly the bounding value Z. We can think of this as the intersection of the hyperplanes defined by Z's. This is a more intuitive definition, I feel, but this is kind of the working definition. It's more useful to, for all of the proofs. This intersection is unique because we are requiring our cones to be simplicial. So all of the rays are linearly independent. So all of the things orthogonal to them will have a specific unique intersection. We say that the coefficient vector Z is cubical if the vector W is contained within the interior of every face of the cone. So I'm using this, this little circle here as you would in like a topology setting to mean the interior. I can relax this condition a little bit by saying that the value is pseudo-cubical by allowing things to be on boundaries. So here I have something cubical. It has to be within this the W here is this dot. So it has to be within the interior of the cone. Here, pseudo-cubical, I'm allowing things to be, can be inside of the cone, but it can also be on the boundary. Here it is for all of these, for the normal complex we saw earlier. And I mean, what I don't want to happen is for the intersection of the hyperplanes to be outside of the cone completely. In this normal complex we saw earlier, the W's, you can see are precisely these, like, the fourth point. I have the vertex, I have the rays, and then I have this fourth point that makes a quadrilateral each time. And so we call this cubicalness because it's giving us an n cube. We've been seeing two-dimensional cones because they're nice to draw and nice to work with, but this also makes sense for three-dimensional cones. And I think this nicely shows this requirement for it to be true for all faces of the cone. So Z is cubical here with respect to all of the faces of the cone. I want it to, for the entire three-dimensional cube, if I have a three-dimensional cone, I want the polytope on it to be a cube. So, the W here would go through the middle for the whole cube, but I also have a bunch of W's here at every two-dimensional face. And the one-dimensional faces also have W's, but they're just like exactly where the Z is. So they're not as instructable. Okay, now we've seen pseudo-cubical values, what this means, and we've defined them the normal complex, the C sigma with respect to an inner product for a given Z. Let's briefly go back to our choice of inner product, which is like, it's a contentious thing. We don't love making choices as mathematicians. But if this theorem is true, which, you could believe me or not, if this is true, if this left side equals the right side, then the choice of inner product didn't matter, because as long as we have a value that's cubical to it, the degree function has nothing, it doesn't account for the inner product at all. And so if these two equal, then regardless of the inner product, the volume is equal. And I mean, I wish I had this. I don't have the coding skills to create an animation for this, but as you change the inner product, the shape of this completely changes. Each polytope gets bigger, smaller, but the volume of the whole complex stays exactly the same. That's crazy. It's crazy that we made this choice and everything is fine. Now, I'm talking about volume. Let's see what volume, what do I mean by this? The vector W, it's pretty clear to see with this three-dimensional figure, it gives us a really nice way to calculate volume. We just have, we split up things into triangles. We just have a bunch of n simplices. So things shouldn't be too bad. There's a little bit of extra care we have to take with how we calculate volume. My cones are, the maximal cones are not top dimensional in the space they live in, right? It's like a line in three-dimensional space doesn't have volume. It doesn't have all of the, it doesn't have the dimensions for it, right? So we are going to calculate volume in this space that's generated by the, in the subspace of each top dimensional cone. The choice of inner product, and when we first learn about inner products, right, it's like we then start measuring things, all of this, right? So the choice of inner product gives us a nice natural volume function. It's just the Euclidean volume. We're going to say it's the Euclidean volume on this space that's going to take our cones and just, calculate the volume in the way we want it to. Just because, in the Euclidean way. So with respect to inner product, it's just looking at all of those, looking at all of the dependencies of them, like doing cross product, doing Kramer's rule, all of that. Any good volume function is just a rescaling of Euclidean volume. So we do just that. We adjust this volume a little bit. We'll denote it with big V and volume function for each cone. It's going to take in a bounded shape, a polytope, and we're going to scale it by the square root of the determinant of the gram matrix. And the gram matrix is just, it's defined for any inner product, where the ijth entry is just the ith row inner product with the jth row. Also, another sanity check, any good volume function should have the unit simplex have volume 1. So the unit simplex in this space generated by our cone is the cone simplex, right? So by saying unit, I'm requiring the length of it to be 1. I'm going to take the union of the ray generators at length 1 and 0. Because all of my rays are linearly independent, the gram matrix will be just 0 on all non-diagonal entries, and then the length squared on the diagonal, that's 1. This is going to be 1. The volume, the Euclidean volume of an n simplex is 1. All is good. Just as we define the volume, the normal complex as the union of polytopes, the volume of the normal complex is going to be the sum of the volumes of polytopes associated to top dimensional cones. So we've defined this volume function. It'll depend on bounding variables of the normal complex. So it'll be a polynomial in 0 variables, just as we wanted. Now, let's go back to this theorem. We are saying that for any pseudo-cubical value z, the volume polynomial equals the volume of the normal complex. The question then becomes is, do pseudo-cubical values exist even? Right, like I can draw them, but like, is this a thing that happens? And to answer this, we turn to all of the nice structure that matroids have by talking about Bergman fans. So the Bergman fan of a matroid, I'll define the matroid by its ground set elements and its lattice of flats. The Bergman fan lives in the space Re that has a basis associated to each element of the ground set, quotiented out by the all ones vector. So it lives in the Euclidean space of one dimension lower than the number of ground set elements. Immediately, this space, we've just quotiented out by one of the basis vectors. It doesn't have a natural basis, and so it doesn't have a natural inner product. So even working with the case of Bergman fans, which maybe are nicer than the general tropical fan, the choice of inner product is already necessary. The Bergman fan is composed of cones associated to flags of flats, where the ray generators of each cone are defined by the flats contained in that flag. I'm going to say that the ray generator of the flag is like the most sensible thing. It's the sum of all of the ground set elements that are in that flat. So the dimension of the cone is the number of ray generators it has, right? And that is going to depend on the length of the flag, of the number of flats in that flag. So let's look at this. This fan that we've been seeing is the Bergman fan associated to this lattice of flats. It has 8 rays, and rays are one-dimensional cones, so they have to correspond to one element flags. The empty set doesn't have a ray generator, right? It's just 0. And the top of our lattice, the flat that's the whole ground set, would correspond to the all ones vector. So that's in our quotient. What we're left with are all of the non-empty proper flats, and they are exactly the rays that we have here. So ray 0 here, everything makes sense, hopefully. I have 8 rays, 8 non-empty proper flats, so flats in ranks 1 and 2. The 2-dimensional cones of this fan correspond to 2-element flags, so flags between the ranks 1 and 2. We have 9 possible flags like this, 3 emanating from 0, and then 2 emanating from atoms 1, 2, and 3 each. We can see here that the 0th atom has 3, so it's in 3 flags, and we can see 3 cones go through, 3 2-dimensional cones go through it. Same with 1, 2, 3. It has, it's contained in 3 different flags, and here it is in 3 different, contained in 3 different cones. And something like 1 contained in 2 flags, and here it is in just 2 cones. So matroids have a lot of nice structure. Bergman fans are great. Let's use all of that to define a cubical Z. So I take a matroid, let's enumerate its ground set elements from 0 to n, in which case the Bergman fan lives in one less dimension than that, so it lives in Rn. Let's choose a basis for this space. Let's have it be just ray generators for 1 through n, which means that the one that we didn't choose, U0, is just the negative sum of all of the other ray generators. remember we have a Z value associated to each ray of the fan, and rays of the Bergman fan are enumerated by the flats. So we define a Z value for each flat. It's going to depend on the presence of this 0th atom in the flat. But what we're going to do, let's take a look if the 0th element is not in the flat. We take the size of the flat and we subtract some large number to some negative exponent. So it's just going to be some, teeny tiny number that we're adjusting by, but it's the size of the flat minus a little bit of adjustment. And then if 0 is in there, then we take the size of the complement of the flat in the ground set, adjust by pretty much the same thing. This coefficient vector is proven to be cubical with respect to the dot product associated to this basis that we chose. And all of that, we were able to show that all because of nice matroid structures, all of the relations that flats have, and the fan being balanced is crucial to this. And this condition is even too strict. We really only needed this to be pseudo-cubical, but we found a cubical value because we weren't sure if pseudo-cubical would be enough. If I take away this tiny adjustment, then we have a pseudo-cubical value. And these are the Z values that we use to make this figure, this normal complex. I try to make this complex without, when I was working on this, I had kind of two options. I was like, well, I can work on the proof or I can work on this figure. There was maybe a month when I was working on both of these, and I kept working on this figure and I could not make it work at all. It just it always looked unbalanced. There would be a weird point, this crisp edge where all three things intersected. Same with this one. I just I couldn't get it. And then, just eventually I had to refocus, do this proof. And only once I found these values, this figure could be generated. Now, we have found a family of pseudo-cubical values, right? Because if we found this cubical value, we can adjust things within the cone to get a lot of these values. So we found it by our theorem. The volume of this normal complex is the volume polynomial. Let's calculate it. The Chow ring will have a variable for each non-empty proper flat of the matroid. The quotients are elements that are not comparable in our lattice, and also differences of sums of flats that contain one ground set element and a different ground set element. And let's calculate this volume polynomial just as we did before for the complete fan. We get this. It's again a two-dimensional, it's a rank 3 matroid. We do one less than that. We do one less than the rank of the matroid. This is a two-dimensional fan, so the squaring still makes sense. We're going to get a 2 multiplying all of the mixed terms that correspond to flags, or in the same way, we get everything that corresponds to a two-dimensional face, right? And then for the square monomials, we get a -1, just as we did before for the rank 2 flats. We get a -1 for rank 1 flats 1, 2, and 3, and then we get a -2 for 0. This is not too difficult to get. Chris Yer has a very nice way, he has a paper about how to calculate this. And for a rank 3 matroid, there's a really crisp formula that gets this, that we can find this volume polynomial with that. So it's really not too bad. And it gives us the volume of this figure, this funny shape of 3 planes glued along a line. So we've seen that pseudo-cubical values exist, and we were able to expand long known results for complete fans to all tropical fans using the structure of Bergman fans, because really the things that we needed were the things that make these two volumes equal is having a cubical value and having a weighted balanced fan, which the tropical fan has. So some current work on this is done by Laura Novak, Patrick Omovetti, and Dustin Ross. They are working to generalize this result from mixed volumes. And I know that next time the seminar meets on Tuesday, Lauren will be speaking about this. Some other directions that the ideas we developed here can take is looking at Earhart volume. If we can count, if we can count volume, maybe we should be able to count lattice points. Additionally, the cubical values define a cone. Maybe that cone has some interesting structure. Maybe it tells us things about the fan itself or the matrix. Who knows? I think that direction is pretty interesting. And with that, thank you all for coming.
Thanks.